We're going to talk a little bit more about eigenvalues and eigenvectors. So this problem is number 1, part G. It's from your book, and it says find the eigenvalues and eigenspaces, and also the geometric and algebraic multiplicities. So the matrix we have, I'm going to call it A. This is a 3 by 3 upper triangular matrix. To find the eigenvalues, we need to take A and subtract from it lambda times the identity matrix, and this is the 3 by 3 identity matrix. That is, we need to subtract this matrix here. Let's do that. So A minus lambda times I is 1 minus lambda, 1, 1, 0, 2 minus lambda, 1, 0, 0, 1 minus lambda. The next step is to take the determinant of this matrix. Now this matrix is upper triangular. Remember that for an upper triangular matrix, the determinant is just the product of the diagonal entries. So we get 1 minus lambda, 2 minus lambda, 1 minus lambda. I'm going to factor out a negative from each one of these pieces here. And I'll have a negative 1, a negative 1, a negative 1. Multiply them together, I just get a negative 1. Lambda minus 1 squared, lambda minus 2. And this polynomial, we call it P of lambda, and this is the characteristic polynomial. And remember that the eigenvalues are the roots of this characteristic polynomial. So if we set this polynomial equal to 0 and solve for lambda, we'll get that lambda is equal to 1 and lambda is equal to 2. And these are our eigenvalues. Okay, and let's figure out what the algebraic multiplicity is. Remember that the algebraic multiplicity is just the power here and here, which the power here is 1. So the algebraic multiplicity for lambda is 1 is equal to 2, and the algebraic multiplicity for lambda is 2 is 1. Now this is a 3 by 3 matrix, the original matrix here, so the maximum number of eigenvalues we could have is 3, because the characteristic polynomial is going to have it's degree 3. As you can see, if we went ahead and FOILed all of this out, we'd have a negative lambda cubed. That would be the highest power. So if we had a 1 here, we would have another eigenvalue. So an n by n matrix would have at most n eigenvalues. Okay, now we have the eigenvalues. The next thing we want to do is find the eigenspaces. Once we have the eigenspaces, we can find the geometric multiplicity, which is just the dimension of the eigenspaces. So let's erase this piece. We need to recall what we have to do to find the eigenspaces. To find the eigenspaces, remember that it is actually the null space of this matrix here, where lambda is equal to these eigenvalues. So we need to plug in each one of these eigenvalues and find the null space. Okay? So let's do that. So I'm going to put up here, just to recall, this is equal to 1 minus lambda, 1, 1, 0, 2 minus lambda, and then this is 1 minus lambda. So to find let's do lambda is equal to 1. So the 1 eigenspace we need to find the null space of A minus 1 times the identity matrix. So I'm going to plug in 1 here and see what I get. So I need to find the null space of 0, 1, 1, 0, 1, 1, 0, 0, 0. To find the null space, we just need to take this matrix and put it in reduced row echelon form. And notice that this matrix in reduced row echelon form, we just have to subtract the first row from the second row. We can put a little line here, make an augmented matrix. And this says, so this is in reduced row echelon form. Remember, this corresponds to x1, x2, x3. And we see that x2 plus x3 is equal to 0. So x2 is equal to negative x3. And also, there's no restrictions on x1, so x1 is free. And you need to choose one of these to be free, so let's say x3 is free. So now we can come up with the null space. The null space is the span of vectors, so x1 we said is free, so we're going to put an r there, just like a free variable. x2 is negative x3, so let's put an s here and a negative s here. Remember, we're working over the complex numbers. Okay, and now we just need to find a basis for this space. So the basis, let's erase this. Remember, you can always pause the video and copy anything down that you need. So what is a basis for this space? Since r negative s is equal to r times 1, 0, 0 plus s times 0, negative 1, 1, we get that our basis consists of these two vectors. So it's the span of 1, 0, 0, comma, 0, negative 1, 1. And just as a reminder, the basis is just these two vectors. If you put the basis is equal to the span of these vectors, you're actually telling me what the null space is. A basis is just a set of vectors that are linearly independent and span the space. If you put the span of the vectors, then they're no longer linearly independent because you're getting all vectors from those two basis vectors. So when I ask you for a basis, you just tell me these two vectors, but if I ask you for the null space, you would tell me the span of those two vectors. Okay, so we found the null space of this, of A minus the identity matrix, which is the eigenspace of lambda is equal to 1. So we can write this up here. The 1 eigenspace is the span of these two vectors. Let's figure out what the eigenspace for lambda is 2 is equal to. Oh, by the way, for lambda is equal to 1, remember that the algebraic multiplicity was 2. And we said in the last video that the geometric multiplicity, which is the dimension of the one eigenspace, for this case, for lambda is 1, would be 1 or 2. And here it actually happens to be 2. Okay, for lambda is equal to 2, the 2 eigenspace is equal to the null space of A minus 2 lambda. This has algebraic multiplicity 1, so the geometric multiplicity is going to be 1 as well. Okay, so here is our matrix A minus lambda I, so I'm going to put a 2 wherever I see a lambda. So I should get a -1, a 0, and a -1. So I want the null space of the matrix -1, 1, 1, 0, 0, 1, 0, 0, -1. So in other words, I want to put this matrix in reduced row echelon form. Well, we can get rid of this -1 and we can get rid of this 1 here because we have this row 0, 0, 1. So if I do that, I have -1, 1, 0, 0, 0, 1, 0, 0, 0. And then I'm going to make this pivot positive. So I have 1, -1, 0, 0, 0, 1, 0, 0, 0. Remember the null space, just as a reminder, the null space of any matrix C is equal to the set of vectors X, such that if you multiply those vectors by C, you get 0. These would be the set of vectors in C3, so column vectors with complex entries, that 3 complex entries. And to do this, you just need to put a line here and make an augmented matrix. So all of this should be reviewed, how to figure out the null space. So I'm going to put this matrix 1, -1, 0, 0, 0, 1, 0, 0, 0 with this column here, because we're doing, just to remind you, this is what we're doing here is we're multiplying it by x1, x2, x3 and setting it equal to 0, and we're trying to figure out what x1, x2, and x3 are. This is just in case you don't realize what I'm doing here, why I'm putting this line. It's because we're trying to figure out the null space, which here we have the matrix C I was talking about times x is equal to 0. Okay, so we can see that x1 minus x2 is equal to 0, so that says x1 is x2, and also x3 has to be equal to 0. So we have one free variable, we can let it be x2. So then the null space of A minus 2 lambda, 2 times the identity, lambda is equal to 2. This is equal to all vectors that look like R0, where R is a complex number. And that's just the span of 1, 1, 0. Okay? So we can put that at the top. Yep, so for lambda is equal to 1, for lambda is equal to 2, I have it written here. For lambda is equal to 2, we were trying to find the 2 eigenspace, and that is just the span of this vector here. Let's move you up. Okay. So we have the 1 eigenspace and the 2 eigenspace, And you can see that the dimension of the one eigenspace is 2. So that tells us that the geometric multiplicity for the one eigenspace, or for the eigenvalue 1, is equal to 2, and the geometric multiplicity for lambda is equal to 2 is 1. Great. The next thing I want to talk about is, can we have an eigenvalue lambda be equal to 0? Let's recall the properties that we had for an eigenvalue and an eigenvector. We said that A is an n by n matrix, and X is a n by 1 matrix, and if A times X is equal to lambda times X, where X is not equal to 0, then lambda is an eigenvalue and X is an eigenvector. Now here I never said that lambda couldn't be 0. I just said that X cannot be 0. Okay, so the 0 vector is never an eigenvector. However, it's possible for lambda to be equal to 0. I'll show you an example of that in just a second. So the answer is yes. Oops. And what would the characteristic polynomial look like if you had lambda equal to 0? So remember that the characteristic polynomial of a matrix is equal to lambda minus lambda 1 to the m1 times lambda minus lambda 2 to the m2, and so on. Where these lambda 1, lambda 2, all the way to lambda k, they're distinct. So if you had a 0 for one of these lambdas, you would get something like lambda to the m1, lambda minus 3. Let's actually put some numbers in here. So lambda squared, 4th, lambda plus 5, and let's say lambda minus 2 cubed. So if this was your characteristic polynomial, your eigenvalues are 0, 3, negative 5, and 2. And 0 would have an algebraic multiplicity of 2, 3 would have an algebraic multiplicity of 4, negative 5 has an algebraic multiplicity of 1, and 2 has a algebraic multiplicity of 3. So it is possible. Here's an example of well, before we do that, I want to actually give you an example of this. So let me just show you that this is actually possible by giving you a matrix. And it turns out that usually if you do have a matrix with a zero eigenvalue, the matrix itself is singular. So here's an example. This is a 2 by 2 example. Let's say A is the matrix 1, negative 1, 1, negative 1. You can see that this is a singular matrix because the determinant is negative 1 minus 1, which is 0. So the determinant of A is 0, which tells me A is singular. But you can see if I take A and I multiply it by the vector 1, 1, I get 0, 0. Because 1, negative 1, 1, negative 1 times 1, 1 be 1 plus a negative 1, which is 0, and then 1 plus a negative 1, which is 0. So we have a 0 as an eigenvalue, and 1, 1 is in the 0 eigenspace. For this particular matrix. You can see if you multiply everything in here by the same number, you would still get 0 as an eigenvalue. You could also do something like 1, negative 2, 1, negative 2, and if you just put the same entry here, so like a 2 and a 1, so if this was, what I'm saying is if you had 1, negative 2, 1, negative 2, 2, 1, then you get 2 minus 2, and this would also be 0. So this matrix, which is singular 2, it has the eigenvalue 0, and here's a vector in the 0 eigenspace. I think that's pretty neat. So let's move on. So I mentioned in the last video that we're working over the complex numbers, and the reason for this is I want my characteristic polynomials to factor completely. So something like this, if you have a characteristic polynomial, lambda squared plus 1, over the real numbers this doesn't factor. So if you have the polynomial, set it equal to 0, you get negative 1 is x squared, and that doesn't happen in the real numbers, so you would say this is not factorable. But we're going to be working over the complex numbers, and when you have this happening, you can see that x is equal to the square root, positive or negative square root of negative 1, and this is actually by definition I. So the square root of negative 1, if it's been a while since you've seen complex numbers, the square root of negative 1, we define it as I. Let's write that down. Okay, so for something like this, we should be able to factor it. And we're going to say P of lambda is equal to lambda plus I and lambda minus I. Because as you can see, if I set this equal to 0, move over the negative 1 and then take the square root. So we get this lambda is equal to plus or minus I. And so I have two complex eigenvalues. One is a positive I and one is a negative I. And remember, for the characteristic polynomial is lambda minus the eigenvalue. So I'd have lambda minus a negative I, which becomes a plus I, and a lambda minus a positive I, which becomes this. It's interesting that whenever you have a complex eigenvalue, that you're going to have a second one, and it's going to be the complex conjugate of the eigenvalue you found.